Hola amigos, ¿qué tal? Welcome back. In this video, we're going to try to get an answer to the question, when is a 2 by 2 symmetric matrix positive definite? In order to set this question up, let's make some assumptions. So suppose we have a symmetric 2 by 2 matrix. We'll call that matrix K with entries K11, K12, K21, K22. And then the claim that K is symmetric, in other words, K equals K transpose, guarantees that entry 1, 2 is identical to entry 2, 1. So when we take the transpose, they look identical. We're going to try to figure out, when does this matrix satisfy the conditions of positive definiteness? To answer this question, we're going to introduce some simplifying notation. Specifically, instead of referring to the entries using the standard entry notation, let's go ahead and introduce the simplifying notation. We'll say that the entry 1, 1 we'll call letter A. Entry 1, 2 and 2, 1, because they're identical, we'll just call both of those B. And we'll call entry 2, 2 C. In this case, A, B, and C are any real scalars, and I do want to note that this matrix has determinant AC minus B squared. Do you recognize that from your past in quadratic functions? Parabolas? Doesn't that look like a discriminant? We'll talk about that later in this video. For now, though, let's go ahead and recall the definition of positive definiteness for a matrix. Let's develop this definition in general. So we said that an n by n matrix K is positive definite if and only if that matrix satisfies two conditions. The first condition is that K must be symmetric, so K equals K transpose. We're going to call that the symmetry condition. And then the second condition we're going to call the positivity condition, which is if I take any non-zero vector x, of course it has to have n by 1 entries because this is an n by n matrix. If I then look at what we're going to call the quadratic form x transpose kx, for any non-zero vector, if that quadratic form is positive, we say that the matrix is positive definite. So we have symmetry and positivity. Sometimes in shorthand, we'll write that the matrix K is greater than 0 to say that it's positive definite. Let's go ahead and filter this definition through the 2 by 2 matrix K that we're analyzing in this particular situation. Specifically, we had K equal to A, B, B, C, and we want to know, can we determine when this matrix is positive definite? In other words, when the quadratic form x transpose kx is greater than 0 for non-zero x, using analysis of the individual entries A, B, and C. To this end, let's go ahead and assume that we have a non-zero vector x, and let's take a look at the quadratic form, what the actual entries are. So from that standpoint, we say x transpose kx, this is a 1 by 2, 2 by 2, 2 by 1, and we can look at it in this form. When we actually do that multiplication out, there's kind of two different ways to do that. First, we could multiply k by x, in which case we would say we multiply x1 by the first column, x2 by the second column, and we sum them together. That would be a times x1 plus b times x2 in entry 1, 1. In entry 2, 1, we would have x1 times b plus x2 times c, and that would be if we did k times x first, and then of course afterwards we would multiply by x transpose. Since matrix multiplication is associative, we could also do x transpose times k first, which would lead to this row vector, again x1 times row 1, x2 times row 2, add those two together and we get this one. No matter how we do it though, notice that that leads to a scalar valued output because I take a 1 by 2, 2 by 2, 2 by 1. The output is a 1 by 1, and it's a function of two variables. It's actually a polynomial function of two variables. And in fact, it's a quadratic polynomial function of two variables. So specifically, we have a squared term in the first variable, a squared term in the second variable, and then some mixed polynomial term in between. We should mention something really beautiful here. This x transpose kx given by this two variable quadratic polynomial is one example of a much larger class of phenomenon, which we're going to call quadratic forms. So if we have a symmetric matrix, we say that we can define a homogeneous quadratic polynomial in n variables. Homogeneous means that it is centered at 0, 0. We'll talk about that later in this course. But the idea is that I can use my matrix as long as a vector on the left-hand side and a vector on the right-hand side to define a quadratic polynomial in n variables, we'll call that q, as a function of x, where q runs from Rn into R, so it takes n variable input and produces a scalar output with respect to those n variables. That function is defined by this quadratic form, x transpose kx, and we say that the quadratic form is positive definite if and only if the matrix K is positive definite. In other words, if and only if this quadratic form is always positive for non-zero entries. In our 2x2 case, we're saying that the quadratic form associated with our symmetric matrix K can be written as a two-variable quadratic function, ax1 squared plus 2bx1 x2 plus cx2 squared, where variables x1 and x2 are the individual entries of x. I do want to give a shout out for those of you that have taken multivariable calculus. If you remember the concept of a multivariable function and the corresponding quadratic surfaces, I'm going to claim that we can actually control the values of a, b, and c, and those things end up producing a quadratic surface. So specifically right now, if I had an identity matrix multiplied by the scalar 5, so I had 5 in entry 1, 1, and 5 in entry 2, 2. We could visualize the corresponding quadratic form as a quadratic surface, and in this case I think we call this an elliptical paraboloid that faces upwards. And if I change the values of a and c, notice that we could also get the hyperbolic paraboloid, which has a saddle point. We can kind of play around with b and see how that shifts it around. When we're asking the questions, how do the individual entries of the matrix K relate to positivity in the corresponding quadratic form, what we're asking is, when we change the values of a, b, and c, what happens to the shape of the corresponding quadratic surface, and is there a way that we can always guarantee that this thing is positive? Well, if the quadratic form can be modeled using a elliptical paraboloid that points up, that satisfies the positivity condition. We'll talk more about that geometric interpretation later on in this video. For now, what we're going to do is we're going to focus on the algebraic ideas behind positive definite and see if we can study those algebraic ideas just focusing in on this expression for our quadratic form. With that in mind, remember the whole goal is that we want to find a way to figure out when the matrix K is positive definite. That is going to be true if and only if x transpose kx is positive. We know something about squares. So if we look at this original expression of the quadratic form in terms of its two-variable quadratic nature, one question that we might ask is, can we leverage this technique called completing the squares to make this thing look a little bit more beautiful? Specifically, how might we transform the first two terms so that we can write those things as a perfect square? To simplify this a little bit, let's go ahead and factor out an a. So if I factor in an a of the first two terms, I get a outside of quantity x1 squared plus 2 times b divided by a, because I've pulled out an a of that second term. Then I have x1, x2. And then I could ask myself, well, what if we were to just focus on the inside of that parentheses? Could I use complete the square to say something intelligent there? Specifically, if I said, let's go ahead and look at x1 squared plus 2b over a x1, x2, could I add something to this expression in order to write it as a perfect square in the form x1 plus b divided by a x2 squared? For a review of this, you can see previous videos on the method of completing the square in one variable. But one thing that we can do to figure out what we should add is actually take a look at this expression, what happens when we square it. Well, we know that when we square anything, we just multiply the base by itself twice. So x1 plus b over a x2 squared is just that expression multiplied by itself twice. We also know this concept of right distributivity of multiplication over left addition. So I can take this expression and pass it to the first variable, as well as this expression and pass it to the second variable. That's exactly what we've done here. We also have distributivity of left multiplication over right addition. So specifically, we can pass the x1 in here. So that would be x1 squared. And then we have plus x1 times x2 times b over a, because that thing gets hit over to this term. On the second part of this expression, we have x1 times b over a times x2. We got this in that place. And then finally, we have something like b over a x2 times b over a x2. That's b squared over a squared times x2 squared. Notice that the two center terms actually have identical factors. So in particular, when I look at this pure square term, it's going to be x1 squared plus 2 b over a x1 x2 plus b squared over a squared x2 squared. But notice this term actually showed up in some form when we were expanding x transpose kx. Here it is up here. And then the claim is if we were to add something that looks like this left-hand side would turn into a perfect square trinomial, and we could factor it at this perfect square. This implies that everywhere I see the expression x1 squared plus 2 b over a x1 x2, we could actually add 0, but in a very special form. I like to call this the mathematician's favorite trick. The idea that we add 0, but we write it in a form that allows us to express our mathematical relationship in a form that is easier to see some properties. So specifically, we can always add 0. That 0 is going to be in the form b squared over a squared x2 squared minus the exact same term, because if I add and subtract the same number, that goes to 0. Once I do that, I can kind of group the first three terms together, and we've just seen that that thing is a perfect square trinomial in two variables. Specifically, I can rewrite that first three terms as a perfect square. Those first three terms are x1 plus b over a x2 quantity squared. When I do that, I have to track the idea that in order to add this term, I simultaneously had to subtract it. So outside of this perfect square, I do have this term of negative b squared divided by a squared x2 squared. So this expression ends up being identical to this expression, one perfect square and some extra information, which was the cost of getting this factored form. But remember, the goal here is to figure out what this all means in terms of the quadratic form x transpose kx. We wrote that in entry by entry definition here, and we've just done some work to get it down into this form. When we factor out an a of the first two terms, I get that exact expression that we've studied in the last few minutes. And then the claim that we made is if we simply added b squared divided by a squared times x2 squared and subtracted the same number inside, that actually leads to a perfect square trinomial in the first three terms, which can be rewritten as a perfect square. So specifically, if I group those first three terms together, I can write that as a perfect square, and I make sure to track the a outside. The second bit of information on the inside of this parentheses came from the idea that these two things combined to give 0, which allowed me to say that these were equal. But specifically, I could distribute the a to that second term. Notice that a times b squared divided by a squared x2 squared, the a on top and the a squared on the bottom cancel out one copy of a, and I'm left with minus b squared over a times x2 squared. Of course, I also have this c x2 squared that was remaining from the original quadratic form that I had, so I want to track that those things are here. But notice this is super powerful because now I have a pure square in the first term and a coefficient times a pure square in the second term. One of those has to do with the two variables combined. The other one is a pure second variable squared. In fact, I can simplify the algebra here and just combine these together by finding a common denominator. So we say that the quadratic form could be written in terms of perfect squares as a times quantity x1 plus b over a x2 squared plus ac minus b squared divided by a times x2 squared. As a friendly reminder, there's something really special going on in the numerator of the coefficient for the second variable squared. Remember that k we wrote as a, b, b, c, which means that the determinant of that matrix is a times c minus b squared. That determinant actually shows up in the numerator of the scalar in front of the second coefficient squared. We're going to come back to that in just a little bit. The point of this discussion, though, is that we are seeing that when we have a 2 by 2 symmetric matrix, the property of the matrix being positive definite, we can translate into a quadratic form, which, via the process of completing the squares, we can write as a scalar times some quantity squared, plus some other scalar times another quantity squared. So the question that we want to ask ourselves is, when is this quadratic polynomial positive? When, for non-zero entries of x1 and x2, does this expression end up being always positive? But notice this expression and the behavior in terms of positivity is dependent on the scalars a, b, and c, which means that we can actually classify positivity of our matrix K based on the behaviors of these scalars. Let's develop this piece by piece. We have just shown that for our symmetric 2 by 2 matrix K, we could write the quadratic form x transpose kx in a perfect square format. Of course, we used completing the square to do that, but we could write that as a outside of quantity x1 plus b over a x2 quantity squared plus ac minus b squared over a times x2 squared. These two terms are always non-negative, and for now, I'm going to introduce some simplifying notation. Let's define a new variable, just a dummy variable y1, which is going to be the inside of the first term squared. So we'll say y1 is x1 plus b over a x2. And then we'll define just some coefficient beta, so a second coefficient, which is given by ac minus b squared over a. Notice that we said that the quadratic form was positive if and only if, with this new notation, we said a y1 squared plus beta x2 squared is positive for non-zero values of x1 and x2. But notice this is a pure quadratic function of two variables squared. The only way that this thing will always be positive is if the scalars a and beta are positive. These two variables squared are always non-negative. We say that the entire expression is positive if and only if at least one of the variables is non-zero, and specifically the values of the scalar a and the value of the scalar beta are positive. It must be that way. In other words, checking positive definiteness of the matrix K is equivalent to checking that both a is greater than 0 and beta is greater than 0, which is given by this expression. However, we already noted that the scalar beta, which was ac minus b squared divided by a, that is the determinant of our matrix K over a, or we could just call that d over a, where d represents the determinant. Here's a claim. If we know the sign of a, then the sign of the determinant actually determines the sign of beta. So if I am given the value of a, I can immediately tell what beta is going to be just by looking at the determinant itself. Let's go ahead and confirm that. Here we have scalars d, a, and beta. D is the determinant of our matrix. A is the scalar in front of the x1 term, or the entry 1, 1 of our matrix. And then beta is this scalar that shows up when we transform our quadratic form into perfect square format using completing the squares. But check this out. Let's assume that we actually knew that A was positive. If we know that A is positive, the question that we want to ask is, well, what do we know about beta? Well, if A is positive and the determinant is positive, we know that a positive divided by positive must be positive. Similarly, if A is positive but the determinant is negative, we know that a negative divided by a positive is negative. Thus, if we know that A is positive, then the sign of beta is identical to the sign of the determinant D. But we said when we look at the quadratic form x transpose kx that we wrote that in this perfect square format, which simplified to this form when we did dummy variable substitutions. And we said that this quadratic form is positive definite if and only if this quadratic function has positive values for a and scalar beta. But this was true if and only if a was positive and ac minus b squared over a was positive. This is equivalent to saying that a is positive. The only way that this scalar is positive, given that a is positive, is if the numerator is also positive. But that's equivalent to say that if the entry 1, 1 of our matrix is positive and the determinant of our matrix is positive, then the quadratic form x transpose kx will always output positive values for non-zero entries of the vector x. And this implies that we actually have a quick check for positive definite of a 2 by 2 matrix K that is symmetric. If I know that K has values A, B, B, C, then in order to check whether or not K is positive definite, I can do a very, very quick check. Look at entry 1, 1, or the value of A. If A is greater than 0, and simultaneously, if the determinant of that matrix is also greater than 0, if AC minus B squared is greater than 0, I immediately know that that matrix is positive definite. I do want to give the geometric interpretation of what's happening here. So imagine that A was 5 and C was 5. That would mean that my matrix K is a diagonal matrix with 5s on the diagonal. The corresponding quadratic surface for our quadratic form, first of all, it goes through 0. That's why we call it homogeneous. There's no upwards or downward shifts, nor is there a left or right shift. That quadratic surface is an upward-facing elliptical paraboloid, which has a unique global minimum. And because it's upward-facing, we say that that thing is always positive as long as we're not down at the bottom of that bowl. That's the statement that the quadratic form is positive definite. Basically, that the corresponding quadratic surface is an n-dimensional version of an upward-facing quadratic polynomial. Notice that if I just go ahead and change the value of C, it does kind of change the curvature. It makes it less impressive. There is something called positive semi-definite, which would happen if the value of C was 0, because the determinant of that matrix is now 0. It's singular, and notice there is no longer a unique global minimum. If I drop C down to negative, notice that we could not say this thing is positive definite, because for some values of x, for some values of our input, this quadratic surface is actually negative. For some values, it's positive. If I go ahead and drop my A to negative, I have what we call a negative semi-definite matrix. The value of B actually kind of changes the way that the surface is structured, but the claim that we're going to make here is that when we change the values of A, B, and C, it kind of changes the behavior of the corresponding quadratic surface. The claim that our quadratic form associated with the symmetric matrix K is positive definite means when we graph that quadratic form as a quadratic surface, we're getting an upward facing elliptical paraboloid that has a unique global minimum. That's kind of the geometry behind what we just did algebraically. I did want to show how you could make your own visualization, your own laboratory experiment to play with the geometry of our 2 by 2 quadratic form in terms of its surface. The stuff that you saw me do in this video, I did in Mathematica, which doesn't have free access. However, if you go to any search engine, I prefer DuckDuckGo because I like privacy. Type in GeoGebra, Geogebra, that is a portmanteau of geometry and algebra stuck together. Go ahead and search that. The first link that you'll get is GeoGebra. That leads you to the home page. Go ahead and find the link that says Powerful Math Apps and it's 3D Calculator. Click on that. That will give us a three-dimensional version of a graph. And in this case, I want to create sliders. So I'm going to create a slider A, I'm going to create a slider B, and a slider C. You could think about these as variable values. Remember, our quadratic form came in the form ax squared plus 2bxy plus cy squared. To do the square, I'm just putting shift caret, so it's shift 6 on my keyboard. Now all of a sudden I have the quadratic surface associated with our quadratic form that we were graphing, and I can start to play with the different values of A, B, and C and how that affects the surface itself. One thing that I would do if I was a student is I would actually take a screenshot of 3 separate integer values for A and D, the scaling coefficient in front of the x term, and then also the determinant, one in which you have positive definite, so the thing is a elliptical paraboloid pointing up, one in which you have a hyperbolic paraboloid, so it has a saddle point, and then one in which it's negative definite. And then I would highlight each of those in my notes so that I could refer back to it. However, this is a really, really fast way for you to make your own visual. The end result of all this analysis is that we have an answer to the question. When is the matrix K, a 2 by 2 matrix that's symmetric, positive definite? Well, the matrix K is positive definite if and only if we know that entry 1, 1 is positive and the determinant of K is also positive. That's going to be a quick check that we use in later portions of this course. For now, let's go on to further explore quadratic forms. I'll see you in the next video.